this is yet another class of diagrams that we could have. And you can imagine this sequence continuing where the main difference is just that I'm going to have more and more different numbers of ricochets happening in the in-between region, whereas I have these arbitrary numbers of ricochets happening within the given regions. So let's just focus, though, on what one of these terms would represent. Let's write down all of the coefficients associated with these, and let's add all of these up and see what sum we get just for this one subset of all of these possible diagrams. So in this case, I would have then a sum, and I'm summing up over all the possibilities where I have n possibilities in the first one and ricochets in the first one and m ricochets in the second. Now for the first one, right, all of these ricochets that I have in here have certain common features that we've seen before. They all transmit in on the plus side, and they all propagate across. Then they either come directly out, or they'll have some number of ricochet factors that's greater than 0 that occur in between. And if I do have a ricochet, I'm going to reflect off of this side, propagate, reflect, propagate. So that's going to be an R minus because it's a downward step when I hit the boundary, propagate, another R minus, another P, just like we've seen before. And this will be to the power n, where n could start at 0 with just going straight through, or would include some number of ricochets. That will then bring me to the last propagation across, and they all end, as we've seen before, with the final T minus. That's the first portion of this history. The next portion always starts then, once I've propagated across the P prime boundary, I now enter into this region, which will then always have a T plus and a P to carry me across to the other side. And just like I had before, I could ricochet, so I'll have an R minus, a P, an R minus, and a P, right? I could ricochet, reflect, propagate, propagate, right? And then, of course, that could happen m times, and then finally I have my final T minus at the end of the day. Now, the beauty of this thing, though, is you will notice that I, of course, can always rearrange my orders of summation following our usual rules, that we can do so at will, so long as the exponent where n or m appears is always written to the right of the corresponding sum. So I'm going to write it as actually a product then of two factors, sum on n, t plus p, r minus p to the n times t minus. Then I will put the summation over m of t plus p, r minus p to the m times t minus. And the reason why I wrote them this way is I hope you will notice that this is exactly the sum that we had carried out for capital T. In other words, all of the possibilities in here, when added up, just give me an overall factor of T. So that's T. And a quick way to see that is if we want it to be very explicit, the first term in the series is my famous T plus T, T minus. And then it's divided by 1 minus the geometric factor, which is the ricochet factor, R minus P. The next term, this sum on M, is going to be a very similar thing. It's a geometric series. The first term when m equals 0 is T plus P T minus, and it's divided by 1 minus R minus P R minus P. And notice I had left out a term, right? This T minus, before the T plus, there was always this P prime in here. So this was times T minus, but then there was the P prime in the middle. So there's a P prime in here. Yes? And this then is, of course, just my capital T. And this is my capital T that arises precisely from the summing over all the possible numbers of ricochets on this side. So this entire diagram, or class of diagrams, when summed over n and m, looks just like a T for this factor, the corresponding P prime for the propagation across the middle, times the T, like so. So yes, indeed, I can simply think of each of these sides, right, as simply a unit that has a net transmission capital T or reflection capital R. And you can run through the same argument if you like to convince yourself that, again, these processes sum to a capital T, these sum to a capital R, this is a P prime, this is again a capital R, this is a P prime. What's nice is that because these bumps are symmetric, the reflection coefficient coming from the right or coming from the left for any individual one is the same. So then this is a P prime, this one is an R. Oh no, this one is a final T, right? Because it's the sum of terms that get me transmitted through. And what I hope you can see then is we are just regenerating the same series that we had before when we had only 2 items. It's exactly the same series, except now the T plus represents the transmission through the barrier on the left, and the T minus represents the transmission through the barrier on the right. This first R minus is transmission, a reflection, against the barrier on the left. And then this R minus is the reflection off the barrier on the right. So then we can simply write down the final result for the 2 bumps is going to be the first term in the series, which now is this term. It has the capital T, treating it as a unit, P prime T, divided by 1 minus the ricochet factor, which is R corresponding to the first bounce off of this side, times P prime, times the R from this side, times the P prime. That lines us up perfectly for either the next ricochet or the final transmission T through the system. That's T2. Then for R2, we have to be just a little careful, but it's not too bad. For R2, you might remember, the series goes like this. The first term is just the reflection off the first barrier. Then I have my geometric series, which involves first this diagram on top divided by the repeating factor, and this diagram always transmits off the first barrier, propagates through, reflects off the back barrier, propagates, and then transmits through the first barrier. So that separates out then just the first reflection off of the first now unit, plus then transmission through the first unit, propagation across. Then when I hit the next side, it's reflection off the far unit, propagation back across, transmission through this side to make it a final net reflection. That's the simplest diagram, and then divided by 1 minus the ricochet factor, RP prime, RP prime. So that then is what happens when I have 2 barriers. Now this is a very powerful idea. It's a way we can group infinite subsets of diagrams together and quickly sum them by simply recognizing that they behave as a single unit. And this is an extremely powerful and important idea that played a very key role in the theory of what's known as quantum electrodynamics. And this idea has a special name. It's called renormalization. It's basically the idea of grouping an infinite subset of terms by simply treating one whole group of terms in my Feynman sums over histories as a single individual unit. And that was a huge part of why Feynman actually won his Nobel Prize. Feynman's Nobel, it was a shared prize, but for his share of the prize, which occurred in actually 1965. So that's our first Nobel Prize idea. So hopefully you kind of were feeling that this was the nice shortcut for handling this problem. If you did, then congratulations. You're, maybe 50, 60 years too late, but hey, you're on the right track.